Mysterious symbols, obscure paths, arcane instructions. No, you haven't opened a map to the lost treasure of Montezuma, you're just trying to wire up a BMS control panel. It can be just as mystifying to understand, not quite as risky to carry out, and nowhere near as financially rewarding as finding real treasure, but the rewards are deeply satisfying. So let's take a tour of a couple of wiring diagrams and see if we can figure out how to decipher them. Now, rather than jumping straight into a full-on BMS drawing and drowning in the detail, we're going to have a look at something a little bit simpler and build up to it. So let's start with this very simple wiring diagram for a DOL starter. When looking at engineering drawings of any kind, you'll find a wealth of information before you even get to the wiring. There's usually what's referred to as the title block. This contains important information such as, surprisingly, the title of the drawing. This time it's the imaginatively named CD DL1/2C DL1/3SE stop. Illuminating stuff. As we'll see in later drawings in this video, they do sometimes have a title that's a bit more straightforward, but this one is coded to describe the starter control. You'll also find on here the company who the drawing belongs to, Crompton Controls, who are supporting this video and can provide you with the solution to pretty much any control problem you have, from the simplest starters through to full-on BMS panels. The drawing also contains an important section over to the right of the page which shows the date the drawing was originally made, in this case back in 1994. It also has these three important boxes that show Crompton Controls have a rigorous quality control system. It shows the initials of the person who produced the drawing, but also crucially, the person who checked the completed drawing and approved it. So the drawing wasn't produced without being checked over and approved by a second set of eyes to make sure it was accurate and fell in line with the relevant standards and company policy. Then we've got the drawing number, and crucially this is usually the file name that is used to save the drawing with. There's also some helpful information about the product the drawing refers to, here in this box pointing out the wiring colours to be used. Mains wiring in black, so the three phases in this case. The control wiring is then in red for AC, and if you should happen to be using DC for the control circuit, then that would be in blue. Now, this might seem baffling to an electrician who's used to working to BS 7671 because these colours seem to be in contradiction to the guidance in that document. That's because as soon as you open up a control panel, you're in a different world and new standards kick in. One of these is mentioned here. It's BSEN 60204-1. This series of documents covers safety of machinery and specifically the electrical equipment of machines. In Regulation 13.2.4, we've got lots of guidance on identifying conductors by colour, and towards the end it recommends exactly what was contained in that box on the drawing. Black for AC and DC power circuits, red for AC control and blue for DC control. Moving to the actual drawing, we've got a physical layout for the controller with the button positions on the front and the internal layout. Generally speaking, this information is likely to be on a separate drawing, especially for large panels. However, this is a small enough drawing to have it all on one page. Keep in mind that if there's something shown on a drawing, it's there for a reason. So looking at this layout diagram, ask yourself, why is it there? It's not to show where to drill the holes for the components or where to fix them because there's no measurements, but it does help us identify the different components with letters and numbers. So on the front of the enclosure, we've got a button here marked EM stop/lock, identified as red in colour. There's also a stop reset button or actuator and a start button too. Inside the enclosure, we've got a device marked 1C for contactor and one marked 1OL for overload. It also shows where the supply and motor connections are made. Now we come to the wiring diagram itself. Generally speaking, wiring diagrams are designed to read like we'd read a page of text in the Western Hemisphere, from left to right and top to bottom. But keep in mind this is a general rule and one that we're going to cheerfully violate later in the video. So we start with the conductors marked L1, L2 and L3, which is where the supply is coming from. This helps us to orientate ourselves with the layout drawing. We're coming in the top of the contactor. If we track these conductors, you can see they head into terminals 1, 3 and 5 of the contactor. We know it's the contactor because it's marked 1C on the wiring diagram, just as it was on the layout diagram. This might seem self-explanatory and even odd to have an identifying number where we've only got one contactor in an enclosure, but it's good practice that gets transferred to panels where you might have a lot of contactors and you need to be absolutely sure you're wiring up the correct one. Out of the bottom terminals 2, 4 and 6 of the contactor, we then connect through to the overload device 1OL. You might think from the wiring diagram that we need to run conductors between the contactor and the overload, but actually the layout diagram shows that they are connected directly together, and indeed the overload has these pins that connect directly to the screw terminals on the bottom of the contactor. Then out of the bottom of the overload from terminals also marked 2, 4 and 6, we head to the motor terminals and the mains connection is complete. Now we can look at the control circuit. If we head back from the mains connection at the top of the contactor along the wires, you can see that they branch off. Now this is a good point to remember, that a wiring diagram does not show the exact relative positions of connections and the routes that wires take within the enclosure. Rather, it shows the terminals laid out in a non-cluttered way and the conductors that join them together. So when you look at the way this conductor branches off L1, you might think that we need to cut the L1 conductor and connect the two wires together at that point. Not so. All it's indicating is that they are joined together somewhere, and the most logical place to do that is in terminal 1 in the top of the contactor. So from terminal 1 we take the conductor, which is handily marked up as being red, and then just trace it to where it makes its next connection. In this case it's terminal 1 on this device, which combines the symbol for a normally closed switch with that of an emergency stop push button, and is handily marked up with emergency stop on the wiring diagram and shown as EM stop lock on the layout diagram. So we can be sure that we're wiring it to the correct one. And then it's just a step and repeat process. Out of terminal 2 of the stop button, we take a red wire to terminal 96 on this button, which is the symbol for a normally closed push button, so a non-emergency stop button, again marked up on both diagrams so we can find it easily. Now just a reminder to look at all the information on the drawing. The stop button contact is also marked up 1 OL underneath the symbol, so the contact for the stop button is actually integrated into the overload. This is a great idea because it means that when the overload operates, maybe because the motor is drawing too much current, it will also disconnect the control circuit and the contact will drop out. Then out of terminal 95 on the overload, we take a violet conductor to terminal 14 on 1C2. Now this is a point where a little confusion could occur because there's no 1C2 marked up on the layout drawing, so where is this? Well, notice there's no button marking of any kind on this symbol, it's just a normally open contact. And if we break down the 1C2 into its component parts, we've got the 1C at the start there, so it must be something on the contactor, and there's a normally open contact on here with terminals marked 13 and 14. This is what's called an auxiliary contact. It's designed and rated to have lower current control connections passed through it, rather than the relatively large currents that pass through the main connections to the load. Now again, notice we've got a funny branch from this violet wire, but it's actually a red wire. Again, we take it from the most convenient terminal, which in this case is probably the auxiliary contact terminal 14, and then we wire it to one side of the start button. Notice it's got the same push button symbol as the stop reset button, but the contact looks a little different. This time it's a normally open device. Now we've very nearly finished wiring the control circuit for this starter, and all we've done every time is look at the next terminal along the drawing and follow the path on here to wherever it goes. Then identify the device and terminal it's connecting to on the drawing and connect those two terminals together in the real world. Simple. We finish up by connecting a red wire from the other side of the start button and a white wire from terminal 13 of the auxiliary contact to terminal A2 down here. Now we've got a new symbol which looks a bit like a resistor, but you can see it's marked up 1C1. So again, breaking that code down, we've got that 1C on there, indicating that it's something to do with the contactor, and in fact it's the solenoid in the back of the contactor that, once energized, generates a magnetic field and closes the contacts, thus connecting the motor. You can see it's marked up with terminals A2 and A1. And let's do it one last time to complete the circuit. Trace the red wire from terminal to terminal on the drawing, so from A1 to L3 via terminal 5 in the top of the contactor, and we connect that up in real life between those 2 points, and we're done. Now, no matter how complicated the circuit, we can just use those simple steps to follow the drawing and connect up the panel. Start from a terminal, trace where the wire goes on the plan, and find the terminal it goes into. Then connect up those two terminals using the correct coloured wire in real life. Do that, and you can't go far wrong. So let's take it up a notch and look at a BMS wiring diagram. This is a wiring diagram from an installation that I've had to redact the information on so that I don't accidentally become a security threat. Genuinely. And the first thing to note is down in this bottom right hand corner, you can see here that this is drawing number 358-25, but this drawing is made up of 33 sheets, of which this is number 2. I can't show you page number 1 as it's the title page and might get me prosecuted. So right off the bat, this is a more complicated drawing and panel, but all we've got to do is apply the same principles as before. We're not going to go through every sheet one at a time because that would make for an Olympically long video, so we'll pick out key points from a selection. One thing to note is that the drawing is so fresh off the pixels that it's been issued for approval, not yet for construction. So some of the final detail, like terminal numbers, will be added later. Now, before we start to trace the wiring, it's a good idea to look at the layout and familiarise ourselves with where things have been positioned. Again, all this will be labelled up for construction purposes, but you can see a few things clearly. Here we've got the isolator for the panel, and below that some MCBs which will be used to distribute current and protect certain pieces of equipment. Other important points of interest include the transformers at the bottom here. We'll see those in use in a minute. Then there's these banks of relay relays here that will allow the BMS controllers below to switch specific loads on and off. And then the final main point of interest here is the banks of terminals at the top of the panel that allow the control panel to connect to the devices that it needs to send power to and communicate with. So let's take a quick look at the first sheet to contain some wiring and do a bit of untangling. Let's violate the first general rule I spoke about earlier and start at the bottom left. There's a little label here with 4 screw holes in the corners that suggests this is actually a label that will be fixed in the panel as a safety warning. That's because these orange wires here will remain live in this panel even when you operate the isolator here. Think of it like the incoming tails to a consumer unit. So the incoming supply cable arrives and connects to the isolator, which is interlocked to the door, so that in theory you can't open this control panel without switching the power off. Notice that it has this shroud around it to prevent you from touching the incoming terminals, which could well remain live. From here, the mains powered conductors are colour coded. You'll notice that there isn't the same handy note we had about control circuit colours on this drawing, and that's because of the increased complexity of this panel. The drawing would become awash with notes and be difficult to understand with information being easily missed. So it's more likely that for this project there will be a separate specification detailing critical information. Tracing the 3-phase conductors around, you can see that the first thing they connect to is a miniature circuit breaker labelled CMCB132A. We can find this on the layout diagram, and again just trace from terminal to terminal and connect the isolator to the MCB. Now, along that connection, you may have noticed that there's a black dot where the conductors branch off the main wiring. This means that those 2 conductors are connected to each other. Not necessarily at the point shown, we shouldn't hack into that conductor and connect them together with chock blocks, but they are connected together, in this case, most likely in the top of the MCB. This is an important point because as the diagrams become more complicated, it becomes impossible to show everything without wires crossing over each other. So, for example, on this part of the drawing, these 2 wires cross over each other, but there's no black dot, and therefore they are not electrically connected to each other. Hopefully by now it's pretty obvious that we just need to take the conductors out of the MCB to the SPD. But there's a bit of the drawing here that looks a bit different to what we've seen so far. The conductors out of these terminals don't seem to connect to anything and just disappear into the ether. So this symbol here shows that these wires don't connect to anything on this sheet, but rather go somewhere else. That somewhere else is shown as sheet 22. If we quickly flip to that sheet, we can see where these conductors end up. Now we'll explain what's on this page in a moment, but for now you can see that these conductors have the same symbol showing a continuation to a different page, and they're labelled up that they're connected to the surge protection status terminals, and at this end they go into terminals 1 and 2 of this device. It's labelled up module number 4, which we can see on the layout drawing here. So we're still just tracing wires from terminal to terminal on the drawing and connecting them up in the panel exactly as we were before, but now we're jumping across pages. Coming back to sheet 2, we can start to unravel the control circuit. Again, it looks daunting, but it's actually pretty simple. We need to take a connection from the surge MCB to this double pole device marked PMCB16A, and coming out the other side of this, we find the very first piece of control equipment. There's a lamp connected across the line and neutral marked with an A, which on this drawing means it's amber in colour. And it also says panel live. If we look at sheet 30, we can see a lamp mounted in the door with a label around it marked up as panel live. So this bit of control couldn't be simpler. When the isolator is switched on and the control circuit MCB is closed, this light will come on to say that this panel is on. Pretty much the simplest bit of control and monitoring that we have on here. While on sheet 2 this looks like a short distance away, we actually need to run these conductors to the door of the panel, which again helps us to understand that a wiring diagram doesn't really pay much attention to the space and distance. It just shows which terminals and devices connect to each other. Also connected to the control circuit MCB is this device, which is a transformer, which we find down at the bottom of the layout diagram and is marked TX1. This is important as there's another transformer on here as well, and we don't want to get them mixed up. This transformer steps the mains voltage down to 24 volts, and therefore all the contactors and other devices should be selected to operate on this voltage. Notice it's still AC though, it isn't being rectified to DC. Notice now that all the control wiring has changed to black, which is entirely acceptable under BSEN 60204. Now this is where the wiring can start to get a bit confusing, both on the drawing and in real life, and so the wires will have these little numbers placed over them at both ends so they can be identified on the drawing. Again, once this drawing goes to the construction version, those numbers will be added. Coming out of the transformer, we've got 2 conductors. One passes through another MCB, this time marked SMCB1 10 amps. The other conductor has no MCB connection, so we can think of these as the line and the neutral for the control circuit. Following the line conductor, we come to our second piece of control equipment, another lamp, this time with a W for white that indicates the control circuit is healthy. Sheet 31 shows the layout of some further signage, and right here we can see a white lamp marked up control circuit healthy. You'll notice that out of the other side of the lamp is the neutral going back to the transformer and completing the circuit. So again, as long as the panel is powered up and these 2 MCBs are on, this lamp should always be lit. Carrying on with the control line, we come to this connection, and following it down we come to this long rectangle with these smaller shapes inside. This is one of those many terminals we saw earlier, so once that connection is made you can see the description of what it's connected to, the fire alarm interlock. Now this is where this type of system gets clever, because it can connect to the fire alarm panel. So this normally open contact here isn't actually within our control panel, it's some distance away, possibly by the front door of the building. When the fire alarm panel is powered up and there's no alarms being sounded, this contact in there is closed and making a connection. That means that tracing it back, this contactor coil marked FR1 is always on when everything's healthy. Now if we scout around on the drawing for some other FR1 marks, we find this normally closed contact here marked FR1/1, which will be open when the fire relay is energized, and this normally open contact here marked FR1/2, which will be closed when the fire relay is energized. It's important to remember again that while these contacts are shown in lots of different places on the wiring diagram, they're all part of one device in the real world. When the fire alarm panel sounds an alarm, the contact in the fire alarm panel will open and the fire relay coil will lose power, causing the two fire relay contacts to change their state. FR1/1 will close and illuminate this lamp, visually indicating the fire alarm has sounded, and FR1/2 will open, disconnecting power to the gas valve, which will then spring back to its closed position. As it does so, a contact in the gas valve will disconnect the control circuit connection to this gas valve relay, causing these contacts here to open and this lamp to illuminate, indicating that the gas valve is closed. And really, we're just repeating the same process over and over for each wire. Where does it come from and where does it go to on the drawing, and then connect those terminals together in the panel. So we won't trawl through every connection, as the principle of getting the information from the drawing to the actual install is clearer now. Instead, let's skip to the BMS part of the control panel. Turning to sheet 17, we find this rather different looking wiring diagram, because now we have devices represented by their physical form rather than symbols. Again, it's pretty simple actually. This is the main controller, and we can find it on the layout diagram here. Looking at the wiring diagram, you can see that it just needs a 24 volt AC supply that this drawing says comes from sheet 16, and sheet 16 shows this supply coming from the transformer TX2. This separates it from the original control circuit and puts all the more sophisticated comms on its own 24 volt supply. So on sheet 17 we see that we take the 24 volt supply to the BMS controller and also to the IQ View 8 display, which is what's referred to as a human machine interface, or HMI. Basically it will display information on the system, but it's not the only way or the main way to program the BMS program. That's done via a remote computer, which can be accessed via the local area network. Sticking with the IQ View 8, you can see these purple dashed lines joining it to the BMS controller and connecting via an RJ45 socket. There's an RJ45 connection to sheet 16 along with the primary network connection. Looking at sheet 16, these connect to a network switch, which then connects to the building LAN and allows for full comms, monitoring and programming to be carried out remotely. Then returning to the other connections for the BMS controller, we can see these RS485 connections. That just means that we use RS485 cable, which is a data cable with twisted pairs, used in this case for a Modbus connection. These just connect from the relevant terminals on the controller to the field terminals, and from there more RS485 is run out to specific connections in the boiler, which enables communication via Modbus. Modbus is just a simple programming language that allows the BMS controller to effectively ask the boiler for specific information that the boiler will then send. The red dashed line down the side indicates that there's shielding in place along the cable that gets connected to the ground terminal of the BMS to prevent the information being transferred from getting corrupted. Moving to sheet 18, we've got a BMS expansion module marked as number 2. In this case, it's made up of universal input-output channels. Very briefly, these are terminals that can be configured to either receive a signal, making them an input, or send a signal, making them an output. The benefit of these types of signal is that they can use 0 to 10 volts control, which is a bit like using a dimmer switch on a light. It can send a signal at a variable voltage, which will make small adjustments to how a device works. So for example, on sheet 19, they're being used to control how much valves on water pipes open and thus control the flow rate of the hot water through them. On sheet 18, they're being used as inputs to measure temperature. This isn't like a thermostat that's either calling for heat or saying I'm hot enough. It's actually communicating a specific message. The water in this pipe is at 40 degrees C. And again, the wiring diagram is simple. It's a shielded RS485 cable from the terminals on the BMS to the field terminations for connection to the sensors in the heating system. Moving forward to sheet 22, we find another expansion module, number 4 this time, but now we've got a slight difference as we're looking at digital input channels. These operate a bit like an old-fashioned doorbell. It can only tell if the button is being pressed or not. These inputs can only tell when a contact is being closed or opened. Now, do you remember ages ago in this video, we looked at the contact on the surge protection device and it came to this sheet? Well, now we see the complete explanation. If the surge protection reaches the end of its service life, it will open the contact inside itself and the signal passing through it from input DI1 on this device will be cut off. The input channel sees this and a piece of programming in the BMS controller will translate this into an alert on the system. So these inputs are digital in the sense that either there's a signal or there isn't, and it will process that information according to how it's been programmed. It won't act as an output, so it can't operate a relay or anything like that. It's just about receiving its dedicated signal. Moving along the drawing, you can see our old friends, the fire, safety and gas relays all have contacts connected to these inputs, so if anything goes wrong and they change state, the BMS controller knows about it. Sheet 26 gives us module 6, which is made up of the exact opposite, namely digital outputs, which again are like standard light switches. They either tell the light to come on or go off. A digital output does the exact same thing, and you can see this from what they're controlling in this case. They go to the boiler and pump connections to say turn on or turn off. Really simple. They don't generally turn them on directly, but rather through a relay or contactor. Otherwise, these devices would have to be really bulky to cope with larger currents flowing through them. So if we follow the connection from DO4, it goes to sheet 11, which shows that the connection passes through DO4 on the BMS expansion module and operates the coil on relay 110. This closes the contact R110/1, which brings the pump online. The pump is receiving its three-phase supply from elsewhere in the panel. So there we go. We've shown we can break a wiring diagram down and follow it pretty simply by just identifying which terminals are connected with which wire and then connecting those terminals together in the physical panel. Even the most complex BMS systems can become less overwhelming by using this approach, and it even helps us to understand how the system is going to operate. And that brings us to the end of this series on BMS control systems. If you're watching on our training platform, then answer the multiple choice questions that follow and you'll receive your certificate for your CPD records. If you're watching on one of our social media channels, then click the link to move over to the free training package and get yourself a certificate, or click this video right here or at the link in the description to see some awesome products and content from Crompton Controls. All that remains in this series of videos is to say thank you very much for watching.